I think the best way to start this off is by defining what exactly conic sections are. Here we go. So a conic section is a curve obtained as the intersection of the surface of a cone with a plane. To put that in normal language, basically, if you have a 3D cone and you run a two-dimensional plane or rectangle through that cone, the intersection that you get between the surface of the cone and the rectangle is a conic section. Now, there are three types of conic sections, with the first type of conic section being an ellipse. Now, what is an ellipse? An ellipse is a curve in a plane surrounding two focal points such that the sum of the distance to these two focal points are constant for every point in the curve, on the curve. Basically, in layman's terms, what that means is that an ellipse is some form of a circular intersection between the cone and the plane. Now, ellipses could be a circle in and of itself, which is when you insert the plane in at a 100 and no at a 90 to, I think it's a 180-degree angle, or it could be more skewed in shape, which is when you throw it in at any other kind of angle. Now, the second type of conic section is the parabola, which is the curve formed from all the points which are equidistant from the directrix and the focus. Now, what that means in layman's terms is that basically a parabola is a symmetrical curve which you can get when you run the two-dimensional plane through the three-dimensional cone. And the line that splits the parabola up the middle is called the axis of symmetry. And finally, the last possible type of conic section is called a hyperbola. Now, you can get a hyperbola when you mirror a cone on top of another cone and then run the two-dimensional plane through the both of them. You run one two-dimensional plane through the both of them, and what you get will be called a hyperbola. Now, the technical definition for that is a symmetrical open curve formed by the intersection of a circular cone with a plane at a smaller angle with its axis than the side of the cone. So what that basically means is that because of those two mirrored cones, you will end up with two symmetrical mirrored parabolas, and that, ladies and gentlemen, is a hyperbola. That's it for the technical definitions of conic sections. Most people assume that calculus and pre-calculus are used generally. You will only see them in math class, but some elements of calculus and pre-calculus do in fact have real-world applications, such as conic sections. You can see an example of conic sections in architecture. A really good example of this would be Roman architecture in particular, because of, you can see it primarily in their aqueducts and bridges, which use parabolas as the support system for the surface of the bridge and the roads, because those are very efficient weight distributing systems. Now, some of those bridges and roadways and aqueducts are still standing after 2,000 years of use and abuse. It can be said that those are pretty efficient ways of building things. But outside of those very niche topics of architecture and mathematical theory, where else can you see conic sections? You can see them in space, of all places. Right now, our planet, with you on it, is moving on an elliptical orbit around the sun, just like every other planet in the solar system, and basically everything in the solar system, which is rotating around the gravitational force of the sun. But a more real-life application of conic sections would be the force of gravity on objects. If you toss an object in the air, it will fall down in a parabolic trajectory towards the ground, because gravity affects the y-axis without affecting the x-axis. An application of that in space would primarily be in use when scientists are attempting to get objects out of our planet's gravitational field into the reaches of outer space. I don't know how this works. Jasper, I don't know how this works. Could you help me out here?
Sure. So, in order to get any objects out of the planetary gravity we have here on Earth, it has to have at least the minimum velocity in order to escape the planet. It's also known as the escape velocity. Escape velocity of an object. And though the exact number is unsure, there is one thing that it's clear. If your speed is under the escape velocity, but high enough such that when you fall to the ground from space, you actually miss the Earth, you would be traveling in either a purely circular orbit or an elliptical orbit around Earth's atmosphere. And this is a property true for almost any case. And the same goes for the other known conic sections, such as the parabola, where if you travel at exactly the escape velocity you need to escape Earth's gravity, you'll be traveling at a parabola relative to Earth, where Earth would be your launch point would be the vertex of this extraterrestrial parabola. And if you were to be, say, higher than the escape velocity necessary to escape Earth's orbit, you would be traveling on a hyperbola straight and away from Earth. And using this, knowing the hyperbola has asymptotes, to which we know that if you travel in that distance, it's sure that you will be roughly in that area, but never more than that. Scientists and space engineers actually use that to make sure that to send the objects in space the right way at the right speed. And with this, we're able to get planetary objects as far as the Oort cloud in the deepest reaches of space, far from our sun. Right?
Okay, so another application of conic sections in space, which is pretty interesting, would be wormholes. Now, what are wormholes? Wormholes are holes in space and time, which are, to some extent, four-dimensional hyperbolas. Because wait, what?
Yeah.
I don't know. Alright, pause this part.
Okay, what happened? Ano ba yun?
I don't know, my mom texted me something, I got distracted.
I am actually out of battery.
A final interesting element of conic sections in outer space would be wormholes. Now, first of all, what is a wormhole? A wormhole is basically a hole in space and time. So basically, it is a four-dimensional cone intersecting our three-dimensionals. Our four-dimensional cone in space and time intersecting our three-dimensional space. So it's theorized that at the other end of the wormhole is a mirrored wormhole in another dimension or universe or whatever you want to call it. So that's another example of a conic section in space. I think that's all we have for today.
Thanks very much. So, this has been Jasper Ferzo, your background artist.
And this has been Reik Tiamsan, your